Today we're diving into the fascinating world of structural stability. Have you ever wondered why some buildings stand tall for centuries while others collapse unexpectedly? The answer lies in the science of stability. In this video we'll explore the principles, forces, and materials that keep structures safe and sound. From ancient wonders to modern skyscrapers, understanding stability is key to engineering success. Let's start our journey by defining what structural stability really means and why it matters in our everyday lives. Structural stability refers to a structure's ability to withstand loads without collapsing or deforming excessively. It's not just about strength, it's about balance and resilience. Engineers analyze how forces like gravity, wind, and earthquakes affect buildings, bridges, and even natural formations. By understanding these forces, they design structures that can handle stress and remain safe over time. This concept is fundamental in architecture and civil engineering, ensuring that our homes, offices, and infrastructure are reliable and secure. Every structure faces a variety of forces, both internal and external. Gravity pulls everything downward, while wind and seismic activity can push or shake structures from different directions. Engineers must predict how these forces interact with materials and shapes. By calculating these effects, they ensure that buildings and bridges can resist movement and maintain their form. This careful balance of forces is what keeps structures standing tall, even in challenging environments. Choice of materials plays a huge role in structural stability. Steel, concrete, wood, and composites each have unique properties that affect how a structure responds to stress. For example, steel is strong and flexible, while concrete is excellent in compression but weak in tension. Engineers select materials based on the demands of the project, ensuring that each component can handle the expected loads. This careful selection is crucial for safety and longevity. How a structure distributes loads determines its stability. Loads can be dead loads like the weight of the structure itself or live loads such as people, furniture, and vehicles. Engineers design frameworks that transfer these loads safely to the ground, often using beams, columns, and foundations. Proper load distribution prevents weak points and ensures that no part of the structure is overstressed, reducing the risk of failure. Shape of a structure greatly influences its stability. Arches, triangles, and domes are classic examples of shapes that efficiently distribute forces. For instance, triangles are inherently stable and often used in trusses and bridges. Curved shapes like arches and domes can carry heavy loads without collapsing. By understanding geometry, engineers create designs that are both beautiful and strong. Strong foundation is essential for any stable structure. Foundations anchor buildings to the ground and spread loads evenly to prevent sinking or tilting. Engineers study soil conditions and choose foundation types like slab, pile, or mat based on the site's needs. Without a solid foundation, even the best designed structures can fail. That's why foundation engineering is a critical first step in construction. Nature offers many examples of structural stability. Trees, bones, and shells have evolved to withstand various forces. For example, tree trunks are flexible yet strong, allowing them to sway in the wind without breaking. Studying natural structures inspires engineers to develop innovative designs that mimic these efficient forms, leading to more resilient and sustainable buildings. Throughout history, humans have built incredible structures that showcase the principles of stability. The pyramids of Egypt, Roman aqueducts, and Gothic cathedrals all demonstrate advanced understanding of materials and forces. These ancient marvels continue to inspire modern engineers, proving that the science behind stability has deep roots in our past. Today's skyscrapers and bridges push the limits of structural stability. Advanced materials, computer modeling, and construction techniques allow engineers to build taller, longer, and more complex structures than ever before. Safety codes and rigorous testing ensure that these modern marvels can withstand extreme conditions, from earthquakes to hurricanes. Balance is at the heart of structural stability. Engineers use mathematical models to predict how forces will act on a structure and ensure that everything remains in equilibrium. This means that all the forces pushing and pulling on a building are carefully balanced, preventing unwanted movement or collapse. Achieving this balance is both an art and a science. Redundancy means designing structures with backup systems, so if one part fails, others can take over. This approach increases safety and reliability. For example, bridges often have multiple cables or beams, so a single failure doesn't lead to disaster. Redundancy is a key principle in modern engineering, ensuring that structures can withstand unexpected events. Not all loads are constant. Dynamic loads like moving vehicles, wind gusts, or earthquakes change over time and can cause vibrations or oscillations. Engineers must design structures to absorb and dissipate these forces using techniques like dampers or flexible joints. This adaptability helps buildings and bridges stay stable under changing conditions. Understanding why structures fail is crucial for improving stability. Engineers study past collapses to identify weak points and design flaws. This process, known as failure analysis, leads to better building codes and safer designs. Learning from mistakes ensures that future structures are more resilient and less likely to experience catastrophic failure. Before construction begins, engineers use models and computer simulations to test how a structure will perform. These tests reveal potential problems and allow for adjustments before building starts. Physical models, wind tunnels, and earthquake simulators are just a few tools used to ensure stability. This proactive approach saves time, money, and lives. Modern engineering also considers environmental impact. Sustainable materials and energy-efficient designs contribute to both stability and ecological responsibility. Green roofs, recycled materials, and smart technologies help create structures that are not only stable but also environmentally friendly. This holistic approach benefits both people and the planet. Even the best designed structures need regular maintenance to stay stable. Inspections, repairs, and upgrades address wear and tear, whether damage and changing needs. Preventive maintenance extends a structure's life and ensures ongoing safety. Engineers and building managers work together to keep everything in top condition. New technologies are constantly improving structural stability. Smart sensors, advanced materials, and automated monitoring systems help detect problems early and optimize performance. These innovations make structures safer, more efficient, and adaptable to future challenges. The field of engineering is always evolving, pushing the boundaries of what's possible. Structural stability isn't just for skyscrapers and bridges. Everyday objects like chairs, bicycles, and playground equipment rely on the same principles. Understanding stability helps us design safer products and environments, from furniture to vehicles. It's a science that touches every aspect of our lives, often in ways we don't even notice. Future of structural stability is exciting. As technology advances, engineers will continue to develop smarter, more resilient structures. From earthquake-proof buildings to self-healing materials, the possibilities are endless. Staying curious and innovative ensures that our built environment remains safe, sustainable, and inspiring for generations to come. In summary, structural stability is a blend of science, art, and innovation. By understanding forces, materials, and design principles, engineers create structures that stand the test of time. The journey of discovery never ends, as each new project brings fresh challenges and opportunities. Thank you for joining us on this exploration of the science behind structural stability. Stay curious and keep building a safer world.